Now the applications of Gauss theorem. As per syllabus, we have to do the 3 applications based on Gauss theorem. So here I have written applications of Gauss theorem. Determination of electric field due to infinitely long uniformly charged straight wire. Infinitely long and uniformly charged. The wire is there which is charged uniformly and it is infinitely extended up to from plus infinity to minus infinity. So due to this, at any point we have to find out the electric field. Second is uniformly charged infinite plane sheet. Infinitely extended plane sheet and which is uniformly charged as well. Due to this also we have to find out the electric field using Gauss theorem. Third is uniformly charged thin spherical cell. Very thin spherical cell is there. And due to it is uniformly charged as well, either positive or negative. Due to this, field inside and outside. At any outside point, field is to be determined. At any inside point, field is to be determined. In here also we can find out the field at the surface as well. Now we are here with electric field due to infinitely long uniformly charged straight wire. Of course thin. So this is the wire of infinite length. It is uniformly charged. Right now I am taking positive, but we can change the sign as per our requirement. Here what we would like to see is, first let lambda equal to linear charge density of uniformly charged wire, and we would like to find out, say, the electric field at a distance r from any point, say O, and this your observation point is P. Now taking OP as radius vector, if we rotate this vector about O, then we would like to get one circular movement of it, and on this we are getting almost identical points as far as electric, or equivalent points as far as electric field is concerned. So here P, say any other point P dash, a third point P double dash, all the 3 points are at equal distance from O. So whatsoever the electric field will be at point P, the same electric field will be seen at P dash and P double dash. Now it is uniformly extended. So will it, the charge on other side or at far away distance will be affecting it? Of course it is affecting. But will that field be radial or something else? That we have to think of. So for this charge or charge over here, the field will be radial, as and when we are going to place any infinitely small test charge, it will be repelled in this direction. But what about the length or the charge which is placed at far away distance on both the sides? So let's try to think over it and do or check what is the effect of these particular elements on the other side or this on both the sides at this point. Assume any small element on both the sides at equal distance. For this element, suppose these two are at same distance, say x. For due to this element, the electric field will be along this, and for this element, the electric field will be along this. Now these two are at equal distance. It's quite obvious this length will also be same, or this distance will also be same. In that case, if equal length element is taken, so the charge amount over here will also be same, say dq. It's quite obvious for same charge amount and same distance, the electric field magnitude will be same. This electric field E is due to this one, here the element, and E dash is due to these elements. First this E dash is due to this one and this E dash due to this one. Now if you take the component, then one component of E dash H is along horizontal. So E dash H due to first, and due to this also E dash H due to second. And their vertical component are also having equal magnitude, E dash V and here E dash V. These two E dash V are of same magnitude, so these two are going to cancel out. So whatsoever the extra electric field this point is getting due to rest of the charge or rest of the sections of the wire, that will always be radial. So it is equally true for all such pairs on both the sides of the given wire. So all the time we can say the field is radial because the vertical components are being cancelled out and horizontal components are being added up. So now we know that electric field is radial due to whole length of the wire. We had just seen it. Now we would like to find out the electric field at a distance r, which is perpendicular distance r from the wire. Here lambda is the linear charge density. We would like to draw a Gaussian cylinder due to its axial symmetry, which wire is also having the same. So if we are going to draw a small length of Gaussian cylinder of length L like this. This length L encloses certain charge that can be determined with the help of this. So here L is the length of Gaussian cylinder and R, either you write radius of Gaussian cylinder or it is also equal to distance of observation point. This point is on the Gaussian surface. Now the total charge enclosed by the Gaussian surface. Now the total charge enclosed by the Gaussian surface, say it is Q enclosed. It is to be determined. We know Q enclosed is the charge inside Gaussian surface. Or enclosed, not inside, charge enclosed, you can say. We know lambda is equal to charge per unit length. We have charge enclosed is Q, E and Cl. Length of the disk is L. So total charge enclosed we have determined, that is lambda into L. This is a charge enclosed by the Gaussian surface. All the time in Gaussian surface, if we are enclosing certain charge, then we know 1 by epsilon naught times the charge enclosed. So phi due to enclosed charge, we know 1 by epsilon naught times the charge enclosed. And that is equal to 1 by epsilon naught times lambda into L. This is first thing. Now we also have the Gauss's law. Phi, from Gauss's law, phi is equal to, we also know this is even the flux, phi equal to integral E dot ds, we know, and you can write dA for area if you are taking. So here this flux is coming out from every place, all parts of the cylinder. So if we are taking a curved surface, the electric field is rightward, area is also rightward. If you are taking the upper cap, upper flat surface of cylinder, any place you take, area is outward normal, so this is dA. And electric field on this side is E. If you can take this side as well. If you, in this side if you take, then this is the dA and this is the electric radial away. And on this is area and this is the electric field away from this, radial away. In the same way, lower cap if you are taking, this is the area outward normal, so this is the area and electric field away. So this is what we have. So total flux is sum of the flux of all the three surfaces. I am writing this as curved surface, this as upper cap, this as lower cap. All the three surfaces I named. Flat one lower cap, flat one upper cap, this is curved surface. So we have lower cap this, upper cap this, and curved surface the whole curve. So first of all, we will find out E dot dA for this, and we integrate for whole. E dot dA for this, we will integrate for whole flat surface. Here also E dot ds for this small element, I am going to integrate. So I am going to write it separately here. First for curved surface I will write. So integration for curved surface. E dot ds or E dot dA. This E dot dA is only for this, and if we integrate, we are getting for whole curved surface. In the same way, if we are going to write integration E dot dA for upper cap, so I am going to write UC upper cap. In the same way, the third one, E dot dA for lower cap. Lower cap means the flux through this. What you see for this is theta equal to 0 degree. For this theta is 90 degree, and for this also theta is 90 degree. So whenever you are finding a dot product with 90 degree cos 90, that reduces 0. Here you are getting curved surface E dA cos 0 degree, E and D are making 0 degree. For upper cap and lower cap, what you are getting? E dA cos 90 degree. This is for upper cap. In the same way for lower cap, E dA cos 90 degree. You know cos 90 is 0, so these two are reducing to 0. You are left with this. And this electric field is constant for all the points of the curved surfaces, as it is radial and this is at equal distance. So it is symmetric, so that is why E is constant, so you can take it out of integration sign. Thus we can write it somewhat like this. So this particular equation reduces to phi is equal to integration E dA for curved surface. You can take it out of integration sign, the E for curved surface, it is integration dA for curved surface. You know that for cylinder, the curved surface area, dA is what? The area of this. And if you are going to integrate, that is the whole curved surface area. For a cylinder of length L, radius R, the curved surface area is 2 pi RL. So you are going to put 2 pi RL. This is also the flux in terms of electric field. Here this is question number 2, the flux in terms of the charge enclosed. So if you are going to compare 2 and 3, what you have, phi and this phi 2 are equal. So 2 and 3 gives E into 2 pi RL for 2, some 3 and 2, 1 by epsilon naught lambda into L. This is 1 by epsilon naught lambda into L. Here L and L cancel out, so E is equal to lambda by 2 pi epsilon naught into R, or E is equal to lambda by 2 pi epsilon naught into, so this is 1 by R, not R, but this is 1 by R. What you are getting, electric field is away. So in this case, if you are using a vector, unit vector with this, in this direction, so you can write this also as E vector is equal to lambda by 2 pi epsilon naught into 1 by R unit vector n. If lambda is greater than 0, E and n are, E is away from this towards normal area vector, and if lambda is, so E is radially away, and if lambda is less than 0, E radially inward. So this is what we have. If you are going to draw the curve E versus R, then in that case here, if you are going to draw E versus R, it is almost equal to this equilibrium. So this is what we have, where lambda is linear charge density and 2 pi epsilon naught. This can also be explained some other way. E is equal to 1 by 4 pi epsilon naught into 2 lambda divided by R. From here you are getting two conclusions. E is proportional to lambda and E is proportional to 1 by R. So if you are going to draw E versus R, you have this particular graph. Here what we had considered in the Gauss's law, that here integral E dot ds, the electric field is due to whole length of a wire, and that I had shown it to you, that in horizontal component added up. Second thing, the charge what we are taking is only due to enclosed charge in the Gaussian sphere. So Q enclosed we are taking, that is also done. Second important point is L tending to infinity is way infinitely extended wire is crucial. We cannot generate it, but L is very large, that can be considered or taken into account. If we are going to find out that midpoint of the length, the electric field, and edge effect or end point effect are ignored, then this formula is almost correct even for very large length of the wire. So these two things must be considered all the time. Now the numericals on infinitely long uniformly charged wire. An infinitely long charge, an infinite line charge produces a field. Line charge is there. Field of 9 to the power 4 Newton per Coulomb. This is electric field is somewhere here. E is equal to 9 into 10 to the power 4 Newton per Coulomb. At distance of 2 centimeter, this is distance 2 centimeter. Find the linear charge density. We know electric field is lambda by 2 pi epsilon naught r. It can also be written as 1 by 4 pi epsilon naught into 2 lambda by r. Now put the values. E is how much? 9 into 10 to the power 4. 1 by 4 pi epsilon naught, you know, 9 to the power 9. 2 lambda you have to find out, divided by r, that r is equal to 2 centimeters, so 2 into 10 to the power minus 2 meter. These are cancelled out, so this 4 10 to the power 5 is left. So lambda is 10 to the power minus 2 into 10 to the power minus 5, that is 10 to the power minus 7 Coulomb per meter. This is the answer. Now the second question, this was in 2018 most probably. Find the work done in bringing a charge Q from perpendicular distance R1 to R2. Any infinitely long uniformly charged wire is also there of linear charge density lambda. So you have to move the charge from R1 to R2. You know the value of electric field is given as lambda by 2 pi epsilon naught r at a distance r. So it's quite obvious electric field is variable with distance. So force on charge is Q into E. So Q into lambda by 2 pi epsilon naught r. It's quite obvious force is also variable. So we have to use the variable force to determine the work done. So for small amount of displacement dr, let the work done is dw equal to f dot dr. F and dr both are in same direction if it is positive, and if we are assuming it so, lambda is not given, so we are assuming treating is positive. So f into dr. F is q lambda by 2 pi epsilon naught r into dr. Now the total work done, from where to where? Moving the charge from R1 to R2. So integrate it. Integrating dw, where r equal to R1 to r equal to R2. Put the value. So constants value you are taking out. So q constant, lambda constant, 2 pi epsilon naught constant. Integration 1 by r dr from R1 to R2. This is q lambda by 2 pi epsilon naught. This is ln r, and it is from R1 to R2. So q lambda by 2 pi epsilon naught, it is ln R2 minus ln R1. So this is equal to q lambda divided by 2 pi epsilon naught ln R2 divided by R1. So that is what the answer is. It was in board's exam, so try to solve it. 2 more questions were given in assignment, try to solve it.